In part one, we talked about why deceleration matters for both performance and injury risk. And in part two, we talked about how we might assess those deceleration capacities. And in this video, then, we're going to talk about monitoring deceleration load. I had this video all planned out, and then yesterday, this new paper came out talking about individualizing acceleration and deceleration thresholds. And it is very relevant to this video, so I will come on to it a little bit later, but now let's start with the foundations of how we capture and monitor decelerations. So like any form of load monitoring, we're trying to quantify exposure to this demand. We talked in the last video about quantifying the capacity and assessing our athletes' ability at decelerating, but now we're tasked with trying to quantify how often and how intensely our athletes are having to brake and having to decelerate in their sport. We do this most commonly with both accels and decels by setting up zones and quantifying how often our athletes completed efforts within those zones, which then also gives us an idea of the intensity of those efforts. But there are many limitations to this approach. Firstly, consider that we are dealing with continuous data, both in terms of instantaneous velocity as well as acceleration. Remember, with our deceleration, it relates to the negative side of our acceleration data. Here then we have an illustration of what this looks like, and this is taken from my article for Sportsmith on the practical guidelines for monitoring decelerations. And you can see then that we have our velocity in the black and our acceleration trace, which when positive is shown in the green and when negative, i.e. decelerating, is shown in the red. This highlights then that in reality, this acceleration is in constant flux. What we're trying to do then is identify discrete efforts from this data. This presents the challenge then of where exactly do we draw the line to be able to define these efforts. To illustrate this further then, we have this plot of speed efforts against acceleration efforts taken from rugby union players' GPS data. You can see that if we define a cutoff at, for example, 4 meters per second squared in the case of acceleration, or conversely, minus 4 meters per second squared for deceleration, we are then drawing a line through a very continuous data set. These absolute cutoffs then group a range of data points into a single category. And in fact, there may be more similarity to data points closer together, say either side of that 4 meters per second squared, but they might be grouped into the same category as, say, a data point that is 4.99 meters per second squared. This challenge of discretization of continuous data is something we face with both our velocity data as well as our acceleration and deceleration data. Similarly, we have a decision as to our setting of our minimum effort duration, which is often also referred to as dwell time. This represents the minimum time required for either our velocity, acceleration, or deceleration effort to be above a certain threshold in order to count as a distinct effort. And this setting really is to help us avoid counting what is a single effort in reality, but oscillates around a threshold as multiple efforts. Whilst it seems to work pretty well with our high-speed data, there is perhaps an even greater challenge with acceleration and deceleration data because so many of these occur at lower duration. Hugo Silva and his colleagues in this study then found that when a minimum effort duration of 0.2 seconds was applied, which is a commonly used dwell time, then only 36% of accelerations and 34% of decelerations were actually captured from the dataset. Ultimately, if our dwell time is set too high, then we'll be missing out on deceleration efforts at the lower duration. So that's definitely a setting to take a look at in your tracking technology. Next up then, we need to decide where to actually set the thresholds for our different bands. And as I've spoken about in the last couple of videos in this mini-series, generally, acceleration and decelerations are coupled together. The thresholds used are symmetrical. Perhaps it might be, for example, 2 meters per second squared, 3 meters per second squared, and 4 meters per second squared for our acceleration, and we use then those same thresholds in negative for deceleration. But I don't think this is necessarily the best approach to have these symmetrical thresholds, because there are different magnitudes in terms of acceleration and deceleration. Consistently across many team sports, athletes reach a higher maximum deceleration than they do their maximum acceleration. That hot off the press publication then illustrates this beautifully with, if we have a cutoff point of 3 meters per second squared for our acceleration and minus 3 meters per second squared for our deceleration, then looking at the actual maximum acceleration and deceleration value hit by one player, for example, this may exceed maximum acceleration by 67%, but given the greater magnitude of their maximum deceleration, this actually exceeds that threshold by 133%. This means then that those arbitrary cutoffs for deceleration may be overestimating the number of efforts relative to acceleration efforts when we are using those same standard thresholds. That is reinforced with this second figure from the Pimenta study. If we look at the highest threshold here, which is greater than plus or minus 5 meters per second squared for acceleration and deceleration respectively, whilst in the green we have 5 efforts above that band for accels, we have as many as 16 for decels, highlighting that perhaps that threshold is too low relative to the maximum capacity in deceleration. Remember also that the very high mechanical demand of a deceleration, that spike in ground reaction force that has to be attenuated very quickly in the initial stage of a deceleration, means that there's greater demand on the musculoskeletal system. It's associated with potentially high fatigue and greater injury risk when not well managed. Therefore, if we are not appropriately capturing our load of our decelerations across these arbitrary bands and potentially underestimating the impact of those high decelerations, then we may not be appropriately using our load monitoring to capture these braking demands in our athletes. But it's not just this difference between the acceleration bands and the deceleration bands, but also the different capacities between our athletes. By using arbitrary bands, our athletes with a higher capacity, a higher maximum deceleration value, then potentially those athletes are getting an insufficient stimulus in terms of their braking load exposure. And conversely, athletes with a lower capacity for deceleration may then be undergoing excessive load that we are underreporting in our data, and maybe as well then getting a disproportionate response in terms of the internal load required for that external load. So in this publication, Ricardo Pimenta and his colleagues are arguing the case for an individualized approach to make those thresholds relative to an individual's capacity. So they are arguing the case for using our individual athletes' maximum acceleration and deceleration captured from our tracking technology within the training environment, and then using relative percentages for our cutoffs. Now, this makes sense physiologically, I think, but it is not without its own limitations. Firstly, the thresholds that they are proposing are currently 0 to 25%, 25 to 50%, 50 to 75%, 75% and above of an individual's maximum deceleration as the high intensity efforts. Those, of course, in themselves are arbitrary cutoffs, and they mention this in their paper and encourage other researchers to investigate what may be the best approach for those cutoffs, even with a relative approach. There is also, of course, the issue of GPS error, which, as previous research has shown us, is potentially greater at those higher acceleration, deceleration demands, which is those events that we're most interested in this case. And calls for individualization of our thresholds with our tracking data is not necessarily a new discussion, but I know Ricardo and his colleagues are doing a lot of work in this space at the moment, calling for individualization approaches across high-speed sprint accels and deceleration data, which should then enable more accurate and appropriate quantification of external load. So I'm reading their research with great interest, and perhaps I'll dive into that even deeper in a future video. That, of course, still doesn't solve our issue of trying to group continuous data. And there have been some other approaches. One tracking provider at the moment has metrics including acceleration load, acceleration density, and acceleration density index, which takes the whole acceleration raw data to better quantify the load on a more continuous basis. That may be a better approach, but again, we have that issue of coupling together acceleration and deceleration. So I'd potentially be interested in seeing maybe some of these approaches diving more specifically into the deceleration side of things. And whilst that may then deal with the issue of bucketing continuous data, we are still potentially obfuscating this continuous data set and reducing it down into one single figure of load, which may be overlooking the nuance and the complexity within an actual training session. So despite all these limitations that we've spoken about in terms of trying to capture how often and at what intensity our athletes are decelerating, it seems for now that this banded approach is still the main focus of our load monitoring. Once we then have comfort around the buckets that we're using, we have awareness of the limitations, but we've actually decided which are the most appropriate bands and dwell time in our specific population, then moving forward, we obviously want to track that over time on a session basis, but then week-to-week basis, a longer, more chronic time frame, as well as looking at changes in the load. I go into more detail on how you can do that in my course, The Fundamentals of Load Monitoring, which is in collaboration with Sport Horizon. So if you're interested in that course, then take a look with the link below. Otherwise, I hope you found this video useful. Please like and subscribe, and I will see you again soon for another Sports Science Insights video.